Now we're going to explore the Turing machine in some depth. We start off with what I like to think of as programming tricks for Turing machines. It's not that anyone is really going to program a Turing machine, but we need to argue about what a Turing machine could do if we really needed to have it do it. That is how we argue about the capabilities of Turing machines. For example, we argue that it can simulate a real computer. Then we delve into the matter of Turing machines with less capability, but the same ability to define exactly the recursively enumerable languages. And we argue that some natural extensions of the Turing machine idea, for example, make them non-deterministic, do not add power. They still accept only the recursively enumerable languages. The conclusion I want to draw from these restrictions and extensions is that the class of recursively enumerable languages is really an important class with many definitions, and that it really does represent what can be computed by any realistic notion of what computation means. And finally, we'll look at some of the closure properties of recursive and recursively enumerable languages. The first programming trick is thinking of the tape as if it had multiple tracks. This idea enables us to describe Turing machines that do things like leave markers on their tape so they can find their way back to an important place. We get k tracks if we think of each tape symbol as a vector with k components, each component chosen from some finite alphabet. We can think of the ith component of each tape symbol as forming the ith track. Input symbols will have the blank symbol in all components but one, which then becomes the track on which the input is placed. Here's how we can visualize a Turing machine with 3 tracks. This symbol is viewed as the vector xyz, but it is really just one tape symbol. Let's suppose the input is written on track 1. Then the input symbol 0 must be thought of as the vector 0 blank blank. And the blank symbol is thought of as the vector blank blank blank. A good use of the idea of tracks is to use one track for data and another track for marks. In the marking track, almost all the tape squares have a blank value, but one or more have special symbols, the marks, that indicate a place on the tape that the Turing machine needs to find later. Here's an example. The bottom track holds the data and the top track is the marking track. This symbol xy represents a marked y. And these symbols are unmarked w and z respectively. A similar trick is to think of the state as a vector, with each component from some finite alphabet. The first component is used to control operation, what we normally think of as the state. But other components are used as a cache to hold values the Turing machine needs to remember. Typically these values are bits or tape symbols, but they can be anything as long as they are chosen from a finite alphabet. Here's an example that will illustrate the 3 tricks we talked about. The Turing machine is not really useful. All it does is copy its input over and over again, moving right on the tape. Here are the values that will appear in the control component of the state, along with the intuition about what they're supposed to be doing. In control state Q, we mark the current position, store the current input symbol in the cache component of the state, and move right. From Q, we also enter the control state P. In state P, we run to the right looking for a blank. When we find it, we deposit the symbol that we've stored in the cache on the data track, and then we move left. From state P, we also enter control state R, in which we run left looking for the mark that was left by state Q. When we find it, we remove the mark, enter state Q, and repeat the process with another symbol. A state is a vector of the form little x, capital Y. Here little x is Q, P, or R, one of the control states, and Y is the cache component. Its values are 0, 1, or B. Incidentally, we shall see that the only state P uses 0 or 1 in the cache. The other 2 states just have the blank in the cache. Thus there are really only 4 states. Tape symbols will be vectors UV. The first component represents the marking track, so U is either X, the mark, or a B, which is no mark. The second component is the data track, so V can be either 0, 1, or B. we regard BB as the blank symbol, B0 as input symbol 0, and B1 as input symbol 1. We'll now describe the transition function of this Turing machine. But before we do, let's understand that A and B can each have the value 0 or 1, but in a rule, all occurrences of one of these letters has the same value. Thus, this is a pair of rules, one for each value of A. It says that if the control state is Q, copy whatever symbol A is on the data track into the cache. That is, this guy winds up here in the cache. The position under the head is marked X, as we see here. And the head moves right, and the control state becomes P. There are two families of rules for control state P. If the current tape symbol does not have a blank in the data track, then stay in the same state, leave the tape symbol as it is, and move right. Note that A and little b can represent either 0 or 1 independently, so there are really 4 rules represented here. When the blank symbol BB is reached, place the symbol A that is in the cache in the data track of the square currently reached. That is, the guy in the cache winds up in the data track. Go to control state R and move to the left. And here are the rules for control state R. In state R, as long as we do not see the mark in the first track, we simply move left with no change in the state or the tape symbol. When we find the square that has the mark, we do 3 things. We remove the mark, we go to control state Q, and we move to the right. We'll be at the position just to the right of where the mark was. We're back in state Q, so the whole cycle will repeat again with whichever input 0 or 1 is in the next square. Here's a motion picture. We are in control state Q with an empty or blank cache, and we're at the left end of the input 0, 1. We're going to pick up the 0 for the cache and mark the current square, going to control state P and moving right. We did all that. Now we failed to see a blank in the data track, so we'll just move right again. Now we see the blank, so we deposit the 0 in the cache and go to state R and move left. Bingo, we haven't found the mark, so we'll move left again. Now here's the mark. We remove the mark, go to control state Q, and move right. And here we are in a situation similar to that in which we started. We'll pick up the 1, mark the square we're at, and move right in state P. Here we go off on another cycle. It never ends. We keep writing 0, 1, 0, 1, 0, 1, so on the data track. We're now going to start exploring restrictions of the original Turing machine model that are powerful enough to simulate the original model, and therefore also define exactly the recursively enumerable languages. Our first restriction is a minor one compared with some of the amazingly strong restrictions we're going to mention later. But this restriction is that we can assume the tape is infinite to the right of the input only. Tape squares to the left of where the input is placed do not exist and may not be used. The Turing machine halts if it tries to move left into a non-existent square, but we shall see that in the construction that simulates a two-way infinite tape by a one-way infinite tape, that it is also possible to design a Turing machine so it never makes that mistake and never falls off the tape. Suppose we have an ordinary Turing machine with a two-way infinite tape. We want to simulate it with a one-way infinite tape. So let's call the initial position of the head square 0. Positions to the left are -1, -2, and so on, heading left, while positions to the right are +1, +2, and so on. The new Turing machine will have 2 tracks on its tape and never move left from position 0. The top track holds the positions 0, 1, 2, and so on of the original Turing machine. And in the bottom track, paired with position 0, is a special marker, a star. It is the presence of this marker that warns the new Turing machine never to go left from that point. Also on the bottom track are all the negative positions of the original Turing machine with position -I paired with position I. That is, the bottom track holds the tape to the left of position 0, but backward. Here's a picture of the new Turing machine. Its state holds the state of the original Turing machine plus a bit, U or L, that tells it whether to look at the upper or lower track to simulate a move of the original. When that bit is U, the new Turing machine moves its head in the same direction as the original, but if the bit is L, then it moves in the direction opposite to that of the original. At the first move, the marker star will be placed on the lower track. However, there is no need to modify the input symbols, since the negative positions of the original Turing machine initially hold blank, and we can treat each of the input symbols and the blank of the new Turing machine as if they had a second component that is blank. There are several other restrictions that are discussed in the text, but we're not going to cover here. It might be surprising, but if you give a pushdown automaton, even a deterministic pushdown automaton, a second stack, then it can simulate a Turing machine. The idea is that one stack holds whatever is to the left of the head, including the head position itself, with the top of the stack at the right end of the string. The second stack holds what is to the right of the head position, with the top of the stack at the left end. The two-stack PDA can figure out a move of the Turing machine. If the head moves left, then a symbol is popped off the first stack and pushed onto the second. If the head moves right, then the top symbol is moved from the second stack to the first. Moreover, an even stronger restriction on the two-stack PDA can be made in addition to determinism. The two stacks can each be a counter, that is, a stack that has only two stack symbols. And one of these symbols, the bottom marker, can only appear as the bottom symbol. Thus the stacks each act like counters. You can add one or subtract one, but you can only tell when the count is 0. You can't tell one large count from another. This comment speaks for itself. The guy who discovered this construction that lets two counters simulate a Turing machine was Patrick Fisher. He was one of the really early computer science professors and apparently attracted the attention of the Unabomber. Pat was sent an exploding package which was opened by his secretary, who was injured in the blast but fortunately survived. Now we're going to look at several extensions to the basic Turing machine that we've described. These extensions have some use when we talk about closure properties of the recursively enumerable languages, but mainly they are considered to convince you that the basic Turing machine is good enough. It captures all of what we might think of as computing by any means. That is, our goal is to simulate each of the extensions with the basic model, and thus to show that the extensions define only the recursively enumerable languages. Our first extension will allow any finite number of tapes. Then we add non-determinism. The last extension is really a demonstration of how a Turing machine can simulate a name-value store. That is, a storage system that lets us associate any value with any name. Recently, very large-scale name-value stores have become a significant factor in the big data world, with systems like Google's Bigtable. However, our purpose here is more mundane. A name-value store is the hardest part of a computer to simulate. In essence, the memory hierarchy of a computer can be thought of as a place where we store values and locations, whether the locations are memory addresses, cache addresses, or block numbers on a disk. If we can show how a Turing machine simulates a general name-value store, then we should have a good idea of how the Turing machine can simulate a real computer. A multi-tape Turing machine has k tapes for some fixed k. There is one head for each tape, and each head is positioned at one square of its own tape. To determine a move of the multi-tape Turing machine, we have to look at the tape symbol under each head as well as the state. And the action of the multi-tape Turing machine consists of a new state, a new symbol for each tape square that is scanned, and a direction for each of the heads. The heads move independently, and some heads may choose to stay where they are rather than move at a step. To simulate k-tapes, we'll use a Turing machine with a single tape, but we'll regard this tape as having two k tracks. K of the tracks are used to simulate each of the k tapes, while the other k tracks are used to mark the head position of each of the tapes. That is, These tracks are blank except for a single X in one of the squares. Here's a picture of a one-tape Turing machine simulating a two-tape Turing machine. There are 4 tracks. 2 of these tracks hold the contents of the 2 tapes, while the other 2 tracks hold only a single X each, marking the positions of the 2 tape heads. That is, the 2-tape Turing machine has the head of its first tape scanning this C, and the head of its second tape is scanning this W. I hope it is clear that the ordinary Turing machine can, to simulate one move of the 2-tape Turing machine, visit each of the X marks, store the symbols that the 2-tape Turing machine sees in cache components of its own state, and finally figure out the move of the 2-tape machine would make. The 1-tape machine then visits each of the positions with the X's again, changes symbols as the 2-tape machine would, and moves the X's to reflect the head moves of the 2-tape machine. The 1-tape machine needs to be careful to remember in a component of its own state how many X's are to its left, so it can always find them all on its own tape. But if we design the 1-tape machine to do that correctly, then it is possible for it to simulate the 2-tape machine, although it will obviously take many of its own moves to do so. Now let's look at the non-deterministic version of a Turing machine. We'll talk only about 1-tape non-deterministic machines, but the addition of several tapes along with non-determinism doesn't add power either. The basic idea is that the Turing machine is allowed to have more than one choice of move for any state tape symbol pair. Once a choice is made, then the next state, new symbol, and head direction are determined. That is, you may have several choices in the non-deterministic Turing machine, but you can't pick a state from one, a symbol from another, and a direction from the third. As for the non-deterministic finite automata and pushdown automata, the non-deterministic Turing machine is said to accept if any sequence of choices leads to an ID with an accepting state. The basic trick is to use the tape of the deterministic machine to represent a queue of IDs of the non-deterministic machine. The deterministic machine will make a systematic search of all the IDs the non-deterministic machine can reach. If it finds one with a final state, then the deterministic machine accepts. But if it never finds one, the simulation may go on forever, but the deterministic machine will never accept. Incidentally, we should start to become aware of a surprising behavior of Turing machines. Sometimes they run forever without accepting or halting. Moreover, we can't tell whether the Turing machine is going to do that or whether it will eventually halt, either accepting or not. That is, you can't tell whether a Turing machine is an algorithm. Anyway, back to our description of how the deterministic Turing machine simulates the non-deterministic. The deterministic machine needs a separate track in addition to the track that holds the IDs of the non-deterministic machine. One purpose of this track is to mark the ID that is currently at the head of the queue of IDs. And we need another mark whose job is to allow the deterministic machine to make a copy of the ID at the queue head, one symbol at a time, while it changes this ID to reflect one of the choices of moves of the non-deterministic machine. Here's a picture of what the tape of the deterministic machine looks like. On the data track, there is a sequence of IDs separated by a special symbol, $, which we assume is not a symbol that can appear in the IDs themselves. The mark X is at the $, just before the ID that is at the head of the queue. The IDs to the left of this point will never be useful again since they have already been processed, but it is more trouble to erase them from the tape than it is to just leave them there. The mark Y indicates the last position of the front ID that has been copied with one choice of move of the non-deterministic machine. The deterministic machine will run back and forth between the Y and the first blank it sees to its right, storing the symbol under the Y in its state and depositing it at the first blank. When it returns to the Y, it moves the Y one position right until it has copied the entire ID. However, making the changes that reflect one move. The process is just a little more complex than the simple Turing machine we gave as our example of the use of multiple tracks, which ran back and forth copying its input. Here's how the deterministic machine processes the front ID on the queue. First, the deterministic machine looks for the state within the front ID. By storing the state and the symbol to its right in its own state, it now knows all the choices of moves for the non-deterministic machine. Suppose there are m choices of move. Then the deterministic machine will create m new IDs at the rear of the queue, that is, to the right of the portion of its tape currently holding IDs. The deterministic machine decides on an order for the m choices and creates an ID reflecting each choice one at a time. After creating all m, it finds the x marker and moves it to the pound sign to the right, thus moving to the next ID in the queue. However, as an exception, if the deterministic machine ever creates a new ID with an accepting state, then it accepts and halts its operation. I described the workings of the deterministic machine fairly informally, but I hope you are convinced that the deterministic machine really could be programmed to do what I suggested. That is, you could write down a delta transition function that did all the things I talked about. However, there is an additional concern that must be addressed. Can we be sure that if any sequence of choices by the non-deterministic machine leads to a final state, then the deterministic machine will eventually follow each ID in the sequence and thus will also accept? To prove that, we first observe that there is an upper bound, say k, on the number of choices of move that the non-deterministic machine has in any situation. Thus, there are at most k IDs reachable after one move, k squared reachable after 2 moves, k cubed after 3 moves, and so on. Suppose the final state is reached after n moves for some n. Then the number of IDs the deterministic machine might have to look at is at most this, which is the sum of the first n powers of k, before it sees the ID with the final state. The exact formula is not important. The point is that k is finite and n is finite, so the number of IDs examined is finite. To see this point, notice that all the IDs reachable after one move are put on the queue before any ID that is reachable by 2 moves, and all the IDs reachable by 2 moves are placed there before we get to any ID that takes 3 moves to reach, and so on. That is, the queue is organized shortest distance first. To summarize, if the non-deterministic machine accepts, it does so in n moves for some finite n. Therefore, the deterministic machine will eventually construct the accepting ID of the non-deterministic machine, even though it may take a number of its own moves that is exponential in n. However, if no sequence of non-deterministic choices leads to acceptance, then the deterministic machine does not accept. Thus, the two machines define the same language. All the constructions we just showed will turn out to be quite useful in the future. We're going to have to do several important constructions involving Turing machines. When we do that, we'll assume the Turing machine that is input is as simple as possible. In particular, we'll assume it is a deterministic machine with one tape, infinite only to the right. However, when we do the simulation, we're free to use a Turing machine that is as powerful as we need. In particular, we can allow it to be non-deterministic and to have as many tapes as we need. But first, let's take up how we simulate name-value stores by a Turing machine. The Turing machine will have several tapes that we'll describe later, but one of the tapes is used to hold the sequence of name-value pairs. As suggested here, the format we use is to separate pairs by pound signs and to separate the name from the value by a star. We assume neither pound nor star are symbols that can appear in any name or value. A second track of this tape will be used to mark the left end of the sequence. This mark never moves, it's just there so we can find the beginning of the sequence and scan it looking for a particular name. A second tape will be used to hold the name that we want to look up. To look up the value associated with a name, use the marker to find the left end of the store. Compare each name with the name on the second tape. If we find a match, then the associated value is between the star and the next pound sign. However, one operation we need to be able to perform on a name-value store is insertion. This operation is like what happens when we store into a computer's memory. When we insert name-value pair NV, if there was no value previously associated with name n, then V will now be associated with n. However, if there was an old value associated with name n, then that value is replaced by v. Regardless of which case applies, the first thing we need to do is to look up the name n using the second tape to hold n as we just discussed. If we scan the entire store and we never find n, then append n star v pound sign to the right end of the store. That is a true insertion rather than a rewriting of a value. But if we find some nv prime in the store, we have to replace v prime by v. If v is shorter than v prime, then you can leave blanks to fill out the value. But the hard case is when v is longer than v prime. Here we have to shift the entire portion of the store that follows far enough to the right to make room for v. Here's how we'll do it. We use a third tape and we copy the entire portion of the first tape that is added to the right of v prime. But make sure to mark the position on the first tape that holds the star to the left of the v prime. Remember, this tape has a second track for marks. Now, write v on the first tape where v prime was. It's okay to overwrite any squares to the right of where v prime was. Then we restore the first tape by copying from the third tape everything that was copied there. The net effect is that the portion of the first tape that held data to the right of v prime has been moved right as many squares as was necessary to fit v in place of v prime. Here's a picture of the sequence of moves. First, we copy everything to the right of v prime onto tape 3. Then we overwrite v on tape 1, covering anything we have to. And then we copy tape 3 onto tape 1, positioning it to the right of whatever space v has taken. Okay, now we're going to see something of the closure properties for both the recursively enumerable languages, that is those that are defined by Turing machines that may run forever if they don't accept, and the recursive languages, those defined by Turing machines that will eventually halt without accepting if they choose not to accept the input. Each of these languages is closed under the regular expression operations union, concatenation, and star. They're also closed under reversal, intersection, and inverse homomorphism. The recursive languages, but not the recursively enumerable languages, are closed under difference and therefore complementation. The recursively enumerable languages, but not the recursive languages, are closed under homomorphisms. Let's first look at closure under union. Let L1 and L2 be languages accepted by final state by Turing machines M1 and M2 respectively. To make things simple, we're going to assume that M1 and M2 are one-tape machines with a semi-infinite tape. For the language L1 union L2, we construct a Turing machine M with two tapes. The first thing M does is to copy its input from the first tape to the second. Then M uses one tape to simulate M1 and the other tape to simulate M2. M accepts if either accepts. To show that the recursive languages are closed under union, observe that both M1 and M2 will eventually halt whether or not they accept. M will accept if either does, but if neither accepts, then M will eventually halt without accepting, so M is also an algorithm. For closure of the recursively enumerable languages under union, we don't know that M or M2 may run forever if they do not accept. If either accepts, then M will surely accept. However, if neither accepts, then M may run forever. But that is okay, since we only want to prove that L1 union L2 is recursively enumerable in this case, not necessarily recursive. We're going to use picture proofs for Turing machines quite a bit. Here's how we represent an algorithm, a Turing machine that always halts. It's just a box with two output signals, accept and reject. We should understand that reject just means that the machine halts without accepting. We know that an algorithm will eventually make one of these signals, and of course not both. Then the design of M can be expressed by this diagram. It gets its input W from the outside, and it feeds it to M1 and M2. which it then simulates. M produces the accept signal if either M1 or M2 accepts. If neither produces accept, then they eventually both produce reject, and M produces the reject signal when they both do. Thus M will make one of these signals but not both, and of course it makes the right signal to accept the union of the languages. And here's how we represent a Turing machine that is not necessarily an algorithm. It makes an accept signal if it accepts, but we cannot expect it to make a reject signal. It may just keep making moves but never accept. This diagram is the design of M for the case where M1 and M2 are general Turing machines. Again, M feeds both the input W. If either raises the accept signal, then M does too. We have no idea what M does if neither accepts, but it doesn't matter. M has the form needed to show that the union of the languages of M1 and M2 is a recursively enumerable language. Here's a picture proof of the fact that recursive languages are closed under intersection. M1 and M2 are algorithms. We design M to feed its input to the simulated M1 and M2, and M accepts if both accept, and M rejects if either rejects. And here's a picture proof for the intersection of recursively enumerable languages. Again, M feeds its input to M1 and M2, and it accepts if both accept. Now, difference and complement give us very different stories for the two classes of languages, recursive and recursively enumerable. If you want to accept the difference of the languages of algorithms M1 and M2, simulate them both until they halt. Accept if M1 accepts and M2 rejects, and otherwise reject. The picture is much like what we saw for union and intersection of recursive languages, only the logic combining the signals is different. An important consequence is that the complement with respect to some alphabet sigma of a recursive language is recursive. Surely sigma star, the set of all strings over sigma, is recursive. So the difference of sigma star and a recursive language is the complement of that language. Unfortunately, this approach does not work for the recursively enumerable languages. They are in fact not closed under difference or complementation. We'll see a particular recursively enumerable language whose complement is not recursively enumerable soon. But just to see why the construction for recursive languages doesn't work, remember that M2 may never halt. So if M1 accepts, we may never know that the input is in the difference. Now let's show that the recursively enumerable languages are closed under concatenation. Let L1 and L2 be defined by Turing machines M1 and M2. Assume M1 and M2 have one semi-infinite tape each. And for concatenation, we're going to construct M, a two-tape non-deterministic Turing machine. Given input W, M guesses a prefix X of W that is in L1. Then let Y be the remainder of W, which then must be in L2, that is, if W is to be in the concatenation of the languages L1 and L2. M moves Y to its second tape. M simulates M1 on input X and M2 on Y. If both accept, then M accepts. Since it is non-deterministic, it will guess every possible way to break W into two pieces. So it always accepts W if W is in L1 concatenated with L2. Next, we claim the recursive languages are also closed under concatenation. We can't use the non-deterministic trick, or at least it's rather hard to do so. However, M will systematically try each possible breakpoint for W into XY. Run M1 on X and M2 on Y. M1 and M2 always halt on each X and Y. If for any breakpoint both accept their pieces, then M accepts. But if all breakpoints lead to rejection by one or both of M1 and M2, then M eventually runs out of things to try and rejects. For closure under star, the same ideas work as for concatenation. Suppose M1 is a Turing machine for some language L, and we want a Turing machine for L star. For the recursively enumerable languages, guess how many pieces to break input W into, and guess where the points of separation are, except if M1 accepts each piece. For the recursive languages, don't guess, but enumerate the breaks systematically, since M1 is guaranteed to halt anytime it is given a piece of the input W to examine. We'll eventually get through testing each of the possible ways to break the input. Reversal is easy for both classes of languages. First, reverse the input and then simulate the Turing machine for language L on the reversed input. We'll not say anything more about this simple idea. Inverse homomorphism is also quite simple. Suppose L is a language, either recursive or recursively enumerable. Let M be a Turing machine for L and let H be a homomorphism. We'll design a Turing machine for H inverse of L. We'll start by applying H to the given input W. Simulate M on H of W. Accept W if H of W is an L. If L is recursively enumerable, then we've got a Turing machine which may not always halt for H inverse of L. But if L is recursive, then we know M will always halt, and thus so will the machine we just designed. Last, let's show that the recursively enumerable languages are closed on their homomorphism. So suppose L has a Turing machine M1. We'll construct a non-deterministic Turing machine M for H of L. Given input W, M guesses a string X and checks that H of X is W. If so, M simulates M1 on input X. If M1 accepts X, then M accepts W. Thus, M accepts H inverse of L. This construction won't work for the recursive languages. The reason is that if H maps some symbols to epsilon, then the string X that M1 accepts may be arbitrarily long, and M may have to simulate an infinite number of possible X's. It can never be sure that there is no X in L for which H of X equals W. Now we are ready to show some particular problems not to have algorithms. The central ideas for this lecture are, first, that Turing machines can be enumerated, so we can talk about the ith Turing machine. That lets us diagonalize over Turing machines the way we diagonalized over languages, showing a particular language that cannot be the language of any Turing machine. Then we establish the principle that a problem is really a language, and we show specific problems not to have Turing machines. To enumerate Turing machines, we're going to develop a specific representation of Turing machines as binary strings. It is sufficient to provide a code for Turing machines whose input alphabet is 0 or 1, although we could encode others if we wanted to. The reason it is sufficient to assume only 0 and 1 are inputs is that Turing machine codes themselves will be binary strings. So we can focus on Turing machines with input alphabet 0, 1 as inputs to other Turing machines with the same input alphabet. The first thing we need to do is to assign integer codes to the components of a Turing machine. We give integers 1, 2, 3, and so on to the states. We'll assume that Q1 is always the start state, and we'll also assume that Q2 is always the one final state of the Turing machine. Notice that once a Turing machine enters a final state, nothing further matters, so we can always merge all final states into one. Thus, we can restrict our attention to Turing machines with a single final state and know that we can still define any recursively enumerable language. The other states will be numbered 3, 4, and so on. The tape symbols are also numbered starting at 1. We'll assume x1 is always the input symbol 0, and x2 is always the input symbol 1. x3 will always be the blank, and any other tape symbols are numbered 4 and above. There are two directions, but we need to number them. D1 is left, and D2 is right. Consider a rule expressed using the integer numbering of the components. That is, the state is Qi, and scanning symbol xj. We'll suppose the Turing machine goes to state Qk, right symbol xl, and moves in direction d sub m. Represent this rule by blocks of I, j, k, l, and m zeros separated by single ones. Notice that all the integers are positive, so the representation for a rule never has consecutive ones. We then represent an entire Turing machine by all its rules concatenated and separated by pairs of ones. Once we have Turing machines represented by binary strings, we can convert these strings to unique integers using the trick we explained a while ago. Put a 1 in front of a binary string and treat the result as a binary integer. Thus, we can talk about the ith Turing machine. And of course, we earlier learned we could talk about the ith binary string. A small matter is that some binary strings represent flawed Turing machines. For example, it might have a pair of double ones with other than 4 single ones between them. That would not represent 5 blocks of zeros and therefore would not represent any move of a Turing machine. However, let's assume any binary string that is flawed represents a Turing machine that accepts the empty language. Likewise, if I is the integer we get from such a string, then the ith Turing machine accepts the empty language. So here is a table relating Turing machines to the strings they accept. The value in row I and column j is 1 if the ith Turing machine accepts the jth string, and 0 if it does not. Notice that if the ith Turing machine is one of the flawed ones, then its rows is all zeros. Any matrix of zeros and ones with rows and columns corresponding to all the integers can be diagonalized over. That is, we can construct an infinite sequence of zeros and ones, call it D, such that the ith bit of D is the complement of the bit in position II along the diagonal. We can argue that D is not a row of the matrix and therefore does not represent the language accepted by any Turing machine. Okay. D can't be row J because it disagrees with the jth row in their jth entries. Thus, D cannot be a row, and therefore the language it describes, the language that contains the ith string if and only if the ith bit of D is 1, is not the language of any Turing machine. Notice that this language can be described as the set that contains the ith string if and only if the ith Turing machine does not accept the ith string. Let's give a name to this language, L sub D, or the diagonalization language. Again, L sub D is the set of binary strings W, such that W is the ith string for some I, and the ith Turing machine does not accept W. We just argued that L sub D is not a recursively enumerable language. That is, it has no Turing machine. We earlier proved that since there are more languages than integers, and since there are no more Turing machines than integers, we already know that there were languages with no Turing machine. But now we're much better off. We have a particular language, L sub D, and a description for this language, such that L sub D is one of the languages without a Turing machine. Note, however, that L sub D is a delicate language. We know what it is, but we can't, for example, always tell whether a given binary string W is in L sub D. To do so, we can figure out the I such that W is the ith string. That's the easy part. Then we can write down the code for the ith Turing machine. In fact, that code is W. If W is the code for a flawed Turing machine, we know it doesn't accept W. But some W's give good codes for Turing machines, and in fact every Turing machine with input alphabet 0 and 1 has at least one code W. We can't always figure out whether a Turing machine is going to accept or to run forever without accepting, so for at least some W's we can never learn whether or not that W is in L sub D. Let us introduce the formal concept of a problem. Informally, a problem is a yes-no question about an infinite number of possible instances of the problem. Here's an example of a problem that is actually quite famous, and we'll see why soon. The instances of the Hamilton cycle problem are undirected graphs. There are an infinite number of graphs, of course. The answer to the question implied by the Hamilton cycle problem is yes, if there is a Hamilton cycle in the graph that is a cycle that passes through each node exactly once. For example, here's a graph that happens to have a Hamilton cycle. It's also got some other edges here and there. But the important thing is it does have the Hamilton cycle in which every node appears once. So formally, a problem is simply a language over some alphabet sigma. Each string in sigma star can be viewed as an instance of the problem once we decide on an encoding for instances as strings. We'll see a number of examples of these encodings, but we already saw one when we encoded Turing machines as binary strings. It should not be hard for you to devise an encoding for graphs in a similar spirit. Then the language associated with the problem is the set of strings that code instances for which the answer is yes. Typically, as we did for Turing machines, our coding allows certain strings that are flawed. They don't really represent an instance. We'll always assume that flawed encodings represent instances for which the answer is no. For example, as a problem, the language LD can be stated, does this Turing machine not accept its own code? When we talk about problems, we use the term decidable. It means that there is an algorithm to answer its question. That is, a Turing machine that accepts the encoded instances of the problem for which the answer is yes, and also halts without accepting the other instances. So a decidable problem is really the same thing as a recursive language, if we think of the language as encoding a problem. The opposite of decidable is undecidable. So here's what we know about languages so far. In the center we see the recursive languages, or as problems, the decidable problems. Then there is a superset of the recursive language called the recursively enumerable languages. These, recall, are the languages accepted by Turing machines with no guarantee that they will halt on inputs they never accept. And then there is outer space, the uncountably many languages that are not recursively enumerable. They have no Turing machine at all. So far we have one example of a language, L sub D, that lives in this region. Remember that the undecidable problems are all those in either the second ring, the recursively enumerable but not recursive languages, or in outer space, that is, everything that is not yellow in this diagram. And a big question we need to answer, are there any languages in the second ring, those that are recursively enumerable but not recursive? And remember, the real goal of our plan is to show some real problems that are undecidable. The fact that L sub D is undecidable, and in fact super undecidable because it is not even recursively enumerable, is interesting, but it doesn't by itself tell us anything about the real world. So here are some examples of real problems that are undecidable. Will a program ever reach a particular line of code? Is a given context-free grammar ambiguous? Are two given grammars equivalent in the sense that they generate the same language? But still staying within the world of Turing machines rather than the real world, but a necessary way station on our trek to the real world, is to show a particular language to be recursively enumerable but not recursive. This is the language we call L sub U, the universal Turing machine language. In more detail, the universal Turing machine takes as input a binary string consisting of the code for some Turing machine M and some input W for M. The universal Turing machine accepts the coded M and W if and only if M accepts W. The idea of the universal Turing machine should not seem strange if you've ever contemplated a Java virtual machine. The JVM takes a coded Java program and an input for that program and executes the program on the input. In fact, the JVM is more general in capability than a Turing machine, which can only make a single accept output. The JVM can cause whatever output the program calls for it to be made. So let's see how to build a universal Turing machine. First of all, inputs to the universal Turing machine are of the form a code for machine M, 3 ones, and then the binary string W. Since a valid code for M can never have 3 consecutive ones, it is never ambiguous what part of the input to the universal Turing machine is M and what part is W. The universal Turing machine accepts its input if and only if that input has a valid code for some Turing machine M, and that Turing machine accepts W. So, for example, the universal machine never accepts a string that doesn't have 3 consecutive ones. We'll design the universal Turing machine as a multi-tape machine. The first tape will hold the input, and we never change that. The second tape is used to represent the current tape of M during the simulation of M with input W. We'll discuss this representation shortly. The third tape of the universal machine simply represents the state of M. The first thing that the universal machine needs to do is to examine its input, and particularly that portion that represents M. It has to check that between consecutive double ones there are always 5 blocks of zeros, and it also has to check that a block of 3 ones appears somewhere on its input, and regards this as the end of the rules for M. Finally, since M is assumed deterministic, the universal machine needs to check that there are never two rules that agree on the first two components. All this checking will require running back and forth on the input quite a bit. It can be facilitated by copying blocks of zeros onto one of the other tapes and comparing these with the rest of the representation for M. If any flaws are found with this code for M, or the 111 is not found, then M is regarded as a Turing machine that accepts nothing, so the universal Turing machine immediately halts and rejects its input. Assuming the code for M is valid, the universal Turing machine next examines the code for M to determine how many squares of its own tape it needs to represent one symbol of M's tape. That is, we discover the longest block of zeros representing a tape symbol, and add 1 to that for a marker between symbols of M's tape. Thus, if, say, x7 is the highest numbered symbol, then we'll use 8 squares to represent one symbol of M. Symbol xi will be represented by I zeros and 7 minus I blanks, followed by a marker #. For example, here's how we'd represent x5. 5 zeros, 2 blanks, and then the #. Now initialize tape 2 to represent the input W. Remember, zeros are x1 and ones are x2. The blanks on the second tape of the universal machine all represent x3, the blank of M, but we won't initialize those squares until we need to. Finally, we initialize tape 3 to hold the start state. That state is always Q1, so it is represented by a single 0. Now we're ready to simulate M. We have the current state on tape 3 and the tape of M represented on tape 2. We scan the moves of M on tape 1 until we find a move that matches both the state and this tape symbol. If we can't find one, then apparently M halts without accepting W, so the universal machine does so as well. But if we find a match, we'll find right after that on tape 1 the new state, which we install on tape 3, replacing the old state. We also find a new tape symbol with which to replace the old tape symbol under the head on tape 2. And we also move the tape head one simulated square of M's tape, left or right, whichever the move says. And most important, if M enters an accepting state, then the universal machine stops simulating and accepts its own input, which, remember, is the pair machine M plus input string W. We claim that the language L sub u is recursively enumerable but not recursive. We just showed that there is a Turing machine for the language L sub u, so surely LU is recursively enumerable. But suppose L sub u were recursive. That means there is a Turing machine that always halts and whose language is L sub u. If that were the case, then L sub d, the diagonalization language, would also be recursive. We're going to explain why on the next slide. But we already know that L sub d isn't recursively enumerable, let alone recursive. So let's assume that L sub u is recursive. We construct an algorithm for L sub d as follows. We're given an input W. Let's suppose W is the ith string. The first thing to do is to check whether or not W is a valid code for a Turing machine. For example, that it doesn't have 3 consecutive ones. If the code is not a valid string, then the ith Turing machine defines the empty language. That means W, the ith string, is not in the language of the ith Turing machine. Therefore, W is in L sub d. Now, suppose W is a valid code for a Turing machine. Then simulate the hypothetical algorithm for L sub u on the input W111W. That bit string represents the ith Turing machine processing the input that is the ith string. Eventually, this algorithm will halt and tell us whether or not the ith machine accepts the ith string. If the algorithm says yes, the ith machine accepts the ith string, then we say no, because that means W is not in L sub d. However, if the hypothetical algorithm says no, then we accept W because W is in L sub d. We proved that there is no algorithm or any kind of Turing machine for L sub d. Therefore, we must blame our assumption. The only thing we assumed without proof was that there is an algorithm for L sub u. That means there really is no algorithm for L sub u. Put these facts together and we conclude that L sub u is really recursively enumerable but not recursive. So here is our improved version of the universe of languages. We still have the decidable problems, or equivalently recursive languages, in the center. Outside, there are two kinds of undecidable problems. The second ring is the languages that are recursively enumerable but not recursive. We now have a concrete example of such a problem, L sub u, the universal Turing machine language. And beyond that is the not recursively enumerable languages, of which we have one concrete example, L sub d. Now we're going to see more undecidable problems. We begin with Rice's theorem, which tells us that almost every question we can ask about the recursively enumerable languages is undecidable. And we then introduce a problem called post-correspondence problem, which we also show is undecidable. Post problem does not appear to have anything to do with Turing machines, so the fact that we can show it as undecidable is a valuable step on our road toward showing real problems undecidable. However, post problem is still just a game, but we can use post problem to show some real problems, for example, questions about grammars, to be undecidable. We'll first see Rice's theorem. That theorem involves what are called properties of languages. Formally, a property of languages is any set of languages, the languages that we say have this property. For example, the property of being infinite is the set of infinite languages. The property of being empty is the set containing only the empty language. While properties like being infinite apply to any language, even not recursively enumerable ones, we need to represent languages, and the Turing machine is the most powerful tool we have for representing languages. So we'll talk about properties of recursively enumerable languages only. So we'll consider a property to be a problem about Turing machines. Given a code for a Turing machine, does it define a language with that property? So for any property P, we can define a language L sub P, the set of binary strings that represent a Turing machine whose language has the property P. So for example, L sub infinite is the set of codes of Turing machines that define an infinite language. There are two properties we call trivial for reasons that will be obvious. For these two properties P, L sub P is decidable. One of these trivial properties is the always false property that contains no recursively enumerable languages. We can think of this property as is not a recursively enumerable language. This property is actually true of some languages, but those are outside the recursively enumerable class, obviously, and we're talking about properties only as applied to the recursively enumerable languages. How do we decide this property? Given an input W, we ignore it and say no. Notice that even if W represents an invalid Turing machine code, we have agreed to take all those strings as representing a Turing machine that accepts the empty language. But the empty language is a recursively enumerable language, so we are correct in saying that W's Turing machine does not have this property. The second trivial property is the always true property. We could express the property as is a recursively enumerable language. The algorithm for this property is to ignore the input and say yes. And Rice's theorem says, for every property P except the two trivial ones, L sub P is undecidable. An important part of the proof of Rice's theorem, which we'll be working on for a while, is the idea of a reduction. There are actually several different notions of reduction. We'll come back to that point later. But the simplest one, and the one we need for Rice's theorem, is an algorithm that takes an input string W for one language, or problem L, and converts it to another string X that is an input to another language or problem L prime, with the property that X is in L prime if and only if W is in L. The value of having such a reduction is that it tells us L is no harder than L prime, at least as far as decidability is concerned. If I know L prime is recursively enumerable, then I also have a Turing machine program for L. If I know L prime is recursive, then I also have an algorithm for L. In either case, the solution for L is to take the input W, convert it to X, see what the Turing machine for L prime does, and take its output to be that answer for W. The thing that turns a string W into X is called a transducer. So far we've only talked about a Turing machine whose only output is the yes or no that is implied by accepting or halting without accepting, respectively. But we can get other kinds of output from a multi-tape Turing machine if we designate one of its tapes to be the output tape and regard what is written there when the machine halts as its output. We could, for example, imagine such a transducer that takes W on its input tape and writes X on its output tape and then halts. So if we reduce language L to L prime using such a transducer, and L prime is decidable, that is, there is an algorithm to test membership in L prime, then there is also an algorithm for L. That is, we start by applying the transducer to input W and producing output X. We apply the algorithm for L prime to input X and decide whether or not X is an L prime. Either way, the algorithm renders a decision, either yes or no. And these two steps form an algorithm for L. The whole thing takes input W and tells us whether or not W is in L. We sometimes see a reduction used to discover an algorithm for L, but the more important use of the idea is in the contrapositive. If we already know that there is no algorithm for L, then there cannot be any algorithm for L prime. That's how we're going to use reductions. We'll take one problem that we may not be interested in, but that we know is undecidable, and reduce it to another problem that we are really interested in, but whose status we don't yet know, and then we will conclude that the second problem is also undecidable. Moreover, when we get to intractability, or the theory of NP completeness, we'll be using reductions that are fast to argue that a problem like L prime can't be solved faster than the problem L. There are more powerful forms of reduction that let us reach the same conclusion. That is, if there is an algorithm for L prime, then there is an algorithm for L. We actually saw one example of a more complex reduction where we started by assuming that there was an algorithm for L sub u, the universal language, and showed how we could then construct an algorithm for LD which we know does not exist. However, the hypothetical algorithm we constructed for L sub d involved more than just turning one string into another. We first had to check whether the input W was a well-formed code for a Turing machine, and if not, we answered the question directly. Moreover, after doing a transduction where we turned input W into W111W, we had to complement the answer that we got from the hypothetical algorithm for L sub u. That is, we turned a yes answer into no, and vice versa. In the simple version of reduction, we are not allowed to modify answers in this way. We have to take whatever answer we get. We'll revisit this issue of more general kinds of reductions when we talk about NP completeness. There, the simple reduction is called a Karp reduction, and more general kinds of reductions are called Cook reductions. Steve Cook and Richard Karp, by the way, were the people who made the earliest contributions to NP completeness theory. We're now ready to prove Rice's theorem. The idea is that we can reduce L sub u to L sub p for any non-trivial property p. Then, since we know L sub u is undecidable, it follows that L sub p is undecidable. Here's how we reduce LU to LP. The input to LU is a Turing machine M and an input W for M. The output will be the code for a Turing machine M prime. That is at least the right form, since LP is a set of Turing machine codes, those for which the language of the machine has property P. Of course, for the transduction from M and W to M prime to work, we must arrange that M prime has property P if and only if M accepts W. That is, M prime is an L sub P if and only if M and W is an L sub U. We'll design M prime to be a two-tape machine. On the first tape, M prime simulates another particular Turing machine which we'll call M sub L on its own input, say X. On the second tape, M prime simulates M on W. It is important to understand that M prime has only its own input X, which the transducer does not deal with, or C. The transducer knows about M sub L. It is built into the design of the transducer, The transducer gets to see the code for M and the string W, that is on its own input. Thus, the transducer can build both the moves of M and the input W into the transition function of the machine M prime, that is its own output. None of M sub L, or W is input to M prime. We're going to assume that the empty language does not have property P. If that is not the case, then consider the complement of P, say Q. Surely the empty language then has property Q, but if we could prove that Q were undecidable, then P also must be undecidable. That is, if LP were a recursive language, then so would be LQ, since the class of recursive languages is closed under complementation. So let L be any language with property P. We know L exists because P is not trivial. Also, let M sub L be the Turing machine that accepts L. Here's how M prime behaves. To begin, M prime writes W on its second tape. It can do that because the transducer, seeing W, generates a sequence of states that write W one bit at a time. M prime, from its start state, enters each of these states in turn. Then M prime moves the tape head for tape 2 to the left end, goes to the start state of M, and simulates W on input W. Again, M prime can do that because the transducer sees both M and W and makes the transition function of M part of the transition function of M prime. Suppose during the simulation of M on W, M enters an accepting state. Then M prime goes to the start state of M sub L and simulates M sub L on the input X to M prime, which has been just sitting there on tape 1 being ignored so far. Where does M prime get the transition function for M sub L? M sub L is a particular Turing machine, one that accepts a language L with property P. Thus, the transducer itself can be designed so that it writes the transitions of M sub L out as part of the transition function of M prime. If M sub L accepts the input X, then M prime enters an accepting state. If M sub L never accepts X, neither does M prime. Thus, if M prime ever gets to the stage where it simulates M sub L, then M prime accepts the same language as M sub L does, that is L. But if M does not accept W, then M prime never gets to the stages where it simulates M sub L, and therefore M prime accepts nothing. Here's a picture to help us remember what M prime does. It first simulates M on input W. So far, M prime's own input, X, is ignored. But if M accepts W, then M prime simulates M sub L on its own input X. And M prime accepts X if and only if X is in L. So to summarize what we know about M prime, first, suppose M accepts W. Then M prime simulates M sub L on X and accepts X if and only if X is in L. That is, if M accepts W, then the language of M prime is L. We know L has property P, so M prime is in LP. Now look at the opposite case where M does not accept W. Then M prime never even starts the simulation of ML, and therefore M prime cannot accept its input X. That is, in this case, the language of M prime is the empty language. We know the empty language does not have property P. Thus, if M does not accept W, M prime is not in the language LP. We conclude that the algorithm we described for converting M and W to M prime is a reduction of L sub U to LP, and therefore that LP is undecidable. That is Rice's theorem. This is a picture that reviews the argument for why the existence of the reduction from LU to LP proves LP is undecidable. We have a real reduction algorithm. I hope you are convinced that you could program this algorithm if you were paid enough. We then contradict the hypothesis that LP has an algorithm by supposing that algorithm existed. Then you could put together the reduction plus the hypothetical algorithm to build an algorithm for LU. Since we already proved that there is no such thing, we have to look at what of this story hasn't been proved. The finger points at the hypothetical algorithm for LP. Since we didn't prove it exists, we just assumed it did. Thus, the assumption must be responsible for the false conclusion. and we can conclude instead that there is no algorithm for property P. Thanks to Rice's theorem, we suddenly have an infinite collection of undecidable problems about the languages defined by Turing machines. Here is just a tiny sample of the questions that are undecidable about Turing machines M. Is M's language regular? Or is it context-free? Does this language include at least one string that is a palindrome, that is, a string that is the same as its reversal? Is the language empty? That is, does M accept any string at all? Does the language contain at least 1,000 strings? But Rice's theorem also applies to programs, since you can write a program to simulate a Turing machine. That tells us any non-trivial question about what a program does will also be undecidable. I want to emphasize about what a program does. There are lots of questions about what a program looks like that are decidable. For example, I can tell whether a program uses more than 20 variable names, but that's not a question about what the program does. An example of a question about what a program does is, does the program eventually halt on any input? That is undecidable. Or, does the program correctly sort its input? That's undecidable. Or, does this line of code ever get executed? That's undecidable. We're now going to take up post-correspondence problem, affectionately known as PCP. PCP is the first example of a problem that is undecidable yet doesn't involve Turing machines or programs, which are really the same thing. As we said, PCP is not really important by itself since it's just a made-up problem, but it leads us to proofs that many other problems are undecidable. These problems are unrelated to Turing machines but are related to matters like context-free languages that were not developed for the purpose of exposing undecidable problems. That is, we studied grammars for their use in matters like describing the structure of programming languages. We had no intent to describe problems that turned out to be undecidable. It just turned out that there were undecidable problems lurking in the theory of context-free grammars. An instance of PCP is a list of corresponding strings. That is, a list of pairs of strings over some particular alphabet sigma. The instance has some number of pairs, say n. The first pair is W1x1, the second is W2x2, and so on. None of these strings can be the empty string. The property of the list that makes the answer to this instance of PCP be yes is that when we take the first component from each pair on the list, that is, Wi1 is actually the first component of the pair that we indexed as I sub 1. I can't draw on the slide two levels of subscripts. Then the second Wi2 is that W from this list that has in the I that is from the I-tooth pair on that list, and so on. Then we get the same string if we take the W's from the pairs as if we took the second components or the X's from the pairs. Okay. Such a list of integers is called a solution to the instance of PCP. Here's a simple example instance of PCP. The alphabet will be 0 and 1. And there are two pairs. The first pair is 0 and 0, 1. The second pair is 1, 0, 0 and 0, 0, 1. Okay. Every time a list of integers has 1, it refers to this pair, and every time it has a 2, it refers to that pair. Okay. In this case, it turns out there is no solution to this instance of PCP. The analysis of this simple instance is not so easy. The easy part is that no solution can start with the second pair. Why? The reason is that if we choose 2 as the first integer in the so-called solution list, then the first string made from the W's that are first components will begin with this 1. But the second string, the one made from the corresponding X's that are the second components, begins with this 0. I don't care how you continue, a string that begins with 1 can never equal a string that begins with 0. However, it is possible that the solution list begins with index 1 because for pair 1 the two strings are not inconsistent, that is, one is a prefix of the other. So let's see if we can build a solution starting with the first pair. Since the two strings are not equal, we have to add another pair. We can't choose pair 1 because the first string would then begin 0, 0, and the second string would begin 0, 1. That could never lead to a solution. So the second index in the solution must be 2. Now both strings begin with 0, 1, 0, 0, and the second string has an additional 1. We're back where we were at the previous choice. We can't pick 1 as the third index, but we can pick 2, and we get a match up to a point, with the second string again having an additional 1. If you think about it, we can never make the two strings be the same, because to do so we'd eventually have to use a pair whose second string was shorter than the first. But there is no such pair in this instance. We conclude that this instance has answer no. On the other hand, let's change the instance a little by adding a third pair, 1, 1, 0, and 1, 0. Now the list of indexes 1, 3 is a solution. From the first strings of the pairs, we get 0 followed by 1, 1, 0, which is 0, 1, 1, 0. That is, 0, 1, 1, 0 is a 0 followed by a 1, 1, 0. From the corresponding second strings, we get 0, 1, that's this, followed by 1, 0, that's that, and that also is 0, 1, 1, 0. In fact, there is an infinity of solutions for this instance. Any string of indexes in the language of regular expression 1 to star 3. That is, after the 1 we can use pair 2 any number of times, including 0 obviously, and finally use the pair 3. So here's the plan for proving PCP is undecidable. We're going to start by introducing a modified version of the problem called MPCP, or the modified post-correspondence problem. The modification is that a solution to MPCP must begin with the first pair, but otherwise the modified and original PCP problems are the same. We'll show how to reduce L sub u, the universal Turing machine language, to MPCP, and then we'll show how to reduce MPCP to P sub p. In fact, this part is easier, so we'll do it first. Just to get the distinction between PCP and MPCP clearer, observe that if we treat the list of 3 pairs from our previous example of PCP as an instance of MPCP, then the answer is yes. The reason is that there is a sequence of indexes beginning with 1, say 1, 3, that produces equal strings from the first and second components of the pairs. But we can reorder the pairs, say by putting 1, 1, 0 and 1, 0 first. As an instance of PCP, order of pairs doesn't matter. There is still a solution. But as an instance of MPCP, there is now no solution. Any solution would have to begin with index 1, but then the first of the two strings would begin 1, 1, 0, and the second would begin 1, 0. So no matter how we extend these strings, they disagree in the second positions, and so they are not equal. Before we can talk about reductions, we need to express PCP and MPCP as languages. The instances of these problems can have any alphabet, so it is not immediately obvious how to express the set of all PCP instances that have a solution. Again, the problem is that there is no finite alphabet for this set, and languages just need a finite alphabet. So we need to code symbols in a finite alphabet. We'll represent the ith symbol of an alphabet by the symbol A followed by I in binary. Thus we only need 3 symbols to represent any number of symbols. The order of symbols of the alphabet is not important. For example, if we have an instance over alphabet A through Z, we could represent A by A1, B by A10, and so on. But we could also represent Z by A1 and Y by A10 and so on. It should be clear that the particular symbols used for the alphabet of a PCP instance does not affect the outcome. And the only other symbols we need to represent instances are the comma and left and right parentheses. Thus, the alphabet for the language of PCP instances will have an alphabet of 6 symbols, the A, 0, 1, comma, left paren, and right paren. Now that we have a finite alphabet for coding instances, we can define 2 languages. L sub PCP, the language of coded instances of PCP that have a solution, and L sub MPCP is the same for the modified problem. Now we can do the reduction of MPCP to PCP. We'll describe the transformation only, but you should be able to visualize the process being performed by a Turing machine transducer. Our input is an instance of MPCP. The output instance of PCP will use the same alphabet as the input instance, plus 2 new symbols, the star and the $sign. Of course, all symbols, the new ones and the symbols in the input instance of MPCP, will be coded using A, zeros, and ones as we just described. For each pair WX in the input instance, there is a pair in the output instance based on W and X. For every first string W of the pair, we add star after every symbol. So, for example, 0, 1 becomes 0 star 1 star. And for X, the second string of the pair, we instead add a star before every character. So, for example, 1, 1 becomes star 1 star 1. The output instance also has a new pair unrelated to any input pair. This pair is $sign paired with star $sign. And the output also has a second pair based on the first input pair. This pair has stars placed after the symbols of the first string and before the symbols of the second string, just like in rules 1 and 2 on the slide. But the first string also has a star at the beginning. So, for example, the pair 0, 1 paired with 0 would become star 0 star 1 star paired with star 0. Here's an example. On the left is the instance of MPCP that is input to the transducer. On the right are those pairs with the added stars. Notice that for each pair, the stars come after the symbols on the first string and before the symbols on the second string. And we always add this pair, which will serve to make the strings of the PCP instance match when there is a solution to the MPCP instance. Its job is to add the missing star to the second string. And this pair also comes from the first pair. It is just like the first pair of the PCP instance, except for the star at the beginning of the first string. Notice that this is the only pair in the entire PCP instance where both strings start with the same symbol. For example, this pair has 0 as the first symbol of the first string and star as the first symbol of the second string. Okay. All these pairs have second strings that begin with star and a first string that begins with 0 or 1. Suppose the MPCP instance has a solution, a sequence of indexes that yield string W when we use the first strings in the pairs and the same string W when we use the second strings. Then we can get a solution to the constructed PCP instance. In this case, the solution string will be W padded with stars before each symbol of W and also at the end followed by the $sign. For example, if W is 101, then the PCP instance's solution is star 1 star 0 star 1 star $sign. To get the PCP solution, we use the same sequence of indexes as in the solution to the MPCP instance with 2 exceptions. First, we use the index of the special pair as the first index. Recall this pair was constructed from the first pair of the MPCP instance with the extra star. And we also add to the solution of the PCP instance the index of the ender pair star, dollar, and dollar to the end of the list of indexes. Thus, a solution to the input MPCP instance means that the output PCP instance also has a solution. But the other direction also holds. If the PCP instance has a solution, we can modify it to get a solution for the input MPCP instance. The first index in the PCP solution must be the special pair because that's the only pair of the PCP instance where both strings start with the same symbol. To change this index to 1, the index of the first pair of the MPCP index. Leave all the other indexes unchanged, but remove from the PCP solution the last index, which must be the index of the ender pair. Why? That's the only pair where both strings end with the same symbol. Thus we've shown that the answer to the questions, does the input MPCP instance have a solution, and does the output PCP instance have a solution, are the same. That means we have a valid reduction from MPCP to PCP. If we can prove MPCP is undecidable, which we'll do next, then we have a proof that PCP is also undecidable. So our next task is to show how to reduce L sub u to MPCP. Given an instance M and W of L sub u, we'll convert this to an instance of MPCP whose only possible solutions yield strings that represent the sequence of IDs that M enters when its input is W. More precisely, suppose this sequence is a sequence of IDs that M enters, starting with the initial ID with input W. Then any solution to the constructed MPCP instance will yield a pair of strings that begin with the sequence of IDs separated by pound signs. However, until M enters an accepting state, when we look at the two strings of the partial solution, one formed from the first strings of the indexed pairs and the second from the second strings of the indexed pairs, the second string will always be a full ID ahead of the first string. Only if M accepts will we be able to choose pairs that make the first string grow faster than the second and eventually make the two strings become identical. We're going to assume, as we can, that the Turing machine M from the input to L sub u has a semi-infinite tape and never moves left from the initial head position. That is, given the actual binary string representing M, we can modify the represented machine to mark its left end of tape, as we did when we described the construction of a Turing machine with a semi-infinite tape from one that had a two-infinite tape. Then we can perform the reduction on the new Turing machine that we know does the same as M rather than on M itself. However, in what follows, we will continue to refer to the input machine as M. The MPCP instance we construct will have an alphabet that consists of all the states and tape symbols of M, or rather the modified M, plus the special marker pound sign. We assume that the symbols used for states and tape symbols are disjoint, so we can tell one from another in the ID. Here's the beginning of the construction of the MPCP instance from M and W. The first pair has a first string that is just a pound sign, but a second string that is the entire first ID with input W, surrounded by pound signs. Note that the transducer gets the CW on its input so it can generate this pair. We'll add the pair pound sign, pound sign. It lets us add markers to the end of one ID in the first string at the same time we add it to the following ID in the second string. Add pair XX for every tape symbol X. This pair lets us add an X to the ID we're forming in the first string at the same time we add an X to the next ID, which is being formed on the second string. Of course, in order to make sure that the strings match, it must be the case that an X appears as the first unmatched symbol of the second string. Recall, the second string is one ID ahead, so these pairs, in effect, let us copy the tape of one ID to the next ID, but prevents us from making changes that are not justified by a move of M. Here's a picture of copying IDs. Suppose we have just reached a point in the sequence of indexes when the second string has a complete ID more than the first string, but otherwise the strings match. We can add to the solution we're constructing the pair AA. That has the effect of putting the first symbol of the new ID at the end of the first string and also extending the second string by the same symbol. That's what we want, since there's no way this A could change in the next ID. We can also then add the index of the pair BB to the solution, extending the new ID one symbol further. This might or might not be the right thing to do. The problem is that If the move of M in state Q with symbol C is to move left, then the second symbol of the new ID is the new state, and B will be the third symbol. But just because we can choose the pair BB doesn't mean we have to. If M is going to move left, there will be another choice of next index that simulates the move correctly, and the sequence where BB is chosen instead will fail to yield a solution to the MPCP instance we're constructing. Now we need to add the pairs that reflect the moves of M. For every state Q in tape symbol X, if the move of M is to the right, say PYR, we have a pair in which Q to the left of X, that's this, can be replaced by a P to the right of Y. That correctly reflects the change in ID that occurs at the rightward move. And if the move is to the left, then we have a family of pairs, one for each symbol Z, that could appear to the left of the state. Note that we arranged that M can never move left from its initial position, so there is no possibility that the state is at the left end of the ID if M moves left. So if the leftward move has state Q and symbol X replaced by state P and symbol Y, then for every Z there is a pair that puts P to the left of the Z and replaces the X by the Y. One other possibility is that in the current ID, the state is at the right end of the ID, scanning a blank we've never visited before. If so, the state will actually be to the left of the pound sign. Okay, and the pairs are almost the same, but when constructing the second string, we should imagine an extra blank in front of the pound sign. The blank is replaced by the new symbol Y, of course. Following a previous example, suppose that in state Q, scanning C, M does indeed move right, going to state P and writing E in place of C. Had M moved left in that situation, the sequence of pair choices would be dead in the water, unable to continue. However, in that case, we could have chosen not to use the pair BB, but instead use a pair that incorporated the left move and handled the B properly. In this case, we have a pair with QC as the first string, so we can match the string on the bottom. It also extends the bottom string with EP, reflecting a move of M. Once the move has been handled, we can just match symbol against symbol. Here the pair DD is used. And once we are at the end of the ID, we use the pair of pound signs to separate the IDs, and we're now ready to continue the sequence of pair choices to copy the new ID, which is ABEPD, and make it changed by another move. But we need some more pairs in the MPCP instance so that in case M accepts, we can find a solution. Note that if M never accepts, then only the rules given so far can ever be used, and these can never lead to a solution because the second string is always one ID longer than the first. However, if M enters a final state F, then it is possible for the F to, we'll say, eat the neighboring symbols of an ID. We no longer have real IDs of M, but it doesn't matter. We've simulated M enough to know that M accepts W, and our only concern then is to make sure that there's a solution to the MPC instance based on M and W. Thus, we add to the instance of MPCP pairs XFYF, FYF, and XFF for all tape symbols X and Y. Using these pairs, together with pairs of the form XX to copy parts of IDs as we have done, we eventually get to an ID that is only the state of F. Of course, that isn't an actual ID of M, but it doesn't matter anymore. And one more pair, F pound pound, paired with the pound sign, will end the two strings being formed, making them the same and yielding a solution to the MPCP instance. So here's an example where M has entered the final state F, and a sequence of choices, either copying a symbol or allowing F to eat the adjacent symbol or symbols, eventually leads to identical strings. So here's what it looks like. Well, we'll just have to copy that A, But now the f can in effect eat the b and c adjacent to it. We have to copy the d, we have to copy the e, we have to copy the pound sign. Now the f can eat the a and the d, but we have to copy the e, we have to copy the pound sign. Now f doesn't have anything that it can eat to its left, but it still will eat the e. And finally, copy the pound sign, and now f pound pound paired with pound makes everything evened up, and we have our solution. Now we know that PCP is undecidable because we successfully reduced L sub u to its own language, M sub PCP. And we're going to reduce PCP to the problem, is a context-free grammar ambiguous? Then, for the first time, we'll have an undecidable problem that arose naturally. That is, not because we were looking for undecidable problems. Before we can talk about any problem involving grammars, we need to find a code for grammars using a finite alphabet, just as we did for PCP. So to start the encoding of grammars, let's represent the ith terminal by symbol A followed by I in binary. That may look like we're thus forgetting what the actual terminal symbols are, but since we're interested in ambiguity, we can rename the terminals any way we like as long as we don't name two terminals the same, and the ambiguity or unambiguity of the grammar will not change. Then we'll represent the ith variable by capital A followed by I in binary. We will assume that A1 is always the start symbol. The right arrow between the head and body of a production will be represented by itself. Likewise, the comma separating productions and the symbol epsilon will represent themselves. For example, this grammar is represented by this string right here. The bar connecting alternative bodies for S has been expanded so that there are two separate productions. This represents S goes to 0S1, and this much represents S goes to capital A. Finally, this represents capital A goes to little c. Suppose we have a PCP instance with k pairs, and let the ith pair be WIXI. We need k index symbols to represent the numbers of the pairs, and we'll use A1 through AK, which we may choose to be symbols that do not appear in the PCP instance itself. Notice that we're going to talk about reducing an uncoded instance of PCP, so it can have any alphabet, to an uncoded grammar, which also can have any symbols. However, the process we describe really takes place with all the symbols coded in the manners we have described. It is easier to follow the construction in the uncoded form, so that's what we'll do. The list language for the first half of each pair, the strings W1 through WK, has a context-free grammar with productions A goes to WI, capital A, little ai. It also has the same sort of production, but with A omitted from the body. The latter kind of productions, these, are used to end the derivations. All the strings in this language are some sequence of the WIs with repetitions allowed and in any order, with the corresponding index symbols following, but in reverse. For example, here's a derivation. Okay, A could derive in one step, let's say W1, A, little a1. And then in one more step, we could use, let's say, the terminal production for W2. So we get W1, W2, and then A2, A1. Notice that the sequence of A's is the reverse of the sequence of W's. And we can do the same thing with the second string from each pair. We'll use variable B and XI's in place of WI's, but the idea is the same. The language of strings generated from A and B each consist of a concatenation of strings, either from the WI's if it's A or the XI's if it's B, and these are the first or second components of the pairs. They're followed by the reverse of the sequence of indexes of the pairs from which these strings came. Here's an example of a PCP instance over alphabet AB. We'll use 1, 2, and 3 as the index symbols. So the grammar with start symbol A is this. For example, the second pair, whose first string is BAA, gives rise to these two productions. Here's BAA with the variable A in the middle, and then 2, which is the index. And then there's another production that's the same but without the capital A. And here's the grammar for the second strings in the pairs with start symbol B. As an example, if we choose the three pairs in order 1, 2, 3, then there's a derivation from A that looks like this. So A, use the first choice, that's this production. Then we'll use the second choice, which is this production, and that gives us A, B, A, capital A, the 2 and the 1. And then we'll use the third pair, but we want to end it, so we'll use that production, and that gives us A, B, A, BBA. That's that. And then 3, 2, 1. We're now ready to show how to reduce PCP to the ambiguity problem. Given the PCP instance, construct the two list languages with variable A for the first strings of the pairs and B for the second strings of the pairs. Then add the productions S goes to A and S goes to B. Of course, S is the start symbol of the grammar. We'll show the resulting grammar is ambiguous if and only if there's a solution to this instance of PCP. But first, let's look at an example that should actually expose how the proof in general works. Here's the grammar constructed from the PCP instance that we saw earlier. It is the sets of A productions and B productions we saw plus the two productions for S. Notice there is a solution 1, 3. That is, the first pair was AAB, and the third pair was BBA with BA. When we take the first strings of each pair, we get ABBA, this, followed by that. And when we take the second strings of each pair, AB and BA, we also get ABBA. And this common string followed by the index string in reverse, which is that, we'll have two leftmost derivations, one starting with A and the other starting with B. Here is the derivation starting with A, and here's the derivation starting with B. So here's the proof this construction is a correct reduction from PCP to ambiguity. First, suppose the PCP instance has a solution, say represented by the sequence of index symbols A1 through AK. Note there can be repeats in this sequence. Then W1 through WK is the same string as X1 through XK. That's what it means for this index sequence to be a solution. Then there are two leftmost derivations of the string that is W1 through WK, or equivalently it's X1 through XK, that is followed by AK down to A1. One starts with S goes to A, and the other starts with S goes to B. For the converse, we're going to show that if there are two leftmost derivations of a string of terminals, then one must begin S goes to A, the other must begin S goes to B. Suppose there are two leftmost derivations that begin with S goes to A. Then we can look at the sequence of index symbols in the resulting terminal string in reverse and learn exactly the sequence of productions used. Except for the last production used, each would be the unique A production that generates the index symbol and has an A in the body. And the final production would be the one with the last, that is leftmost index symbol, and no A in the body. The same idea works for derivations that start with S goes to B. There can be only one with a given sequence of index symbols. Here's an example. If the derivation starts with S goes to A and produces a terminal string with index sequence 2, 3, 2, 1, then here's what the derivation or parse tree has to look like. First of all, we start with A. The first production used must generate the 1 at the right end, and we need to keep the A, so this is the only choice. So we've generated W1 off to the left of the A. The next index symbol from the right end is a 2, so we have to use this production. Again, we still need to keep that A there because we have more index symbols to go. Then the third from the left index symbol is 3, so this is the production we have to use. And then the last index symbol is 2, that is the leftmost index symbol is 2. So we're going to get rid of that A and use this production. That's the only way we could generate a string with 2, 3, 2, 1 at the end and no other index symbols. We can prove many things about context-free grammars to be undecidable as well, but to do so we need to show that the complement of a list language is also context-free. Remember that the complement of a context-free language need not be context-free, but fortunately these are. For the proof, we find it easy to construct a pushdown automaton, in fact a deterministic pushdown automaton, for the complement. The PDA we construct will start with a bottom marker on its stack. At first, some symbols from the PCP instance, not indexed symbols, will appear. The PDA simply pushes them onto the stack. After the first index symbol arrives, start checking that the proper strings appear on the stack. That is, if we see an index symbol AI, then check that the proper WI appears on the stack with the right end of WI at the top. The PDA pops all the symbols of WI if so. Note that we're assuming this is the complement of the list language based on the first components. If it is for the second components, we'll check that XI appears on the top of the stack, again with the right end at the top. What we seem to be doing is accepting the list language itself rather than the complement, but I didn't tell you when the PDA accepts. In fact, it accepts every input, with only the exception of when it has found a string in the list language. That is, if the input so far was some sequence of PCP symbols followed by some sequence of index symbols, and these sequences are not empty, and the bottom of stack marker is now exposed, then the PDA does not accept this string. It will accept any other string that follows, which cannot then also be a solution to the PCP instance. Now we can use the complement language. Let LA and LB be the list languages for the first and second components of an instance of PCP. And let LA complement and LB complement be their complements. Now all 4 of these languages are context-free languages. Let's consider the union of the complement languages. This is also a context-free language by the fact that context-free languages are closed under union. I claim that this union equals sigma star, where sigma is the alphabet consisting of all the symbols used by the languages involved, if and only if there is no solution to the PCP instance. Suppose there were a solution, say represented by the index symbols A1 through AN. Then this string is not in the complement of LA, and the equal string, this, is not in the complement of B. Thus, if there is a solution, there is a string missing from the union. Conversely, suppose string Y AN down to A1, let's say this, is missing from the union. That means Y is the string you get by using indexes A1 through AN and taking the first strings from the index pairs. And it's also the string you get by doing the same with the second pairs. That means A1 through AN is a solution to the PCP instance. We have now reduced PCP to the question, is a given context-free language equal to all strings over its terminal alphabet? Thus, this problem is undecidable. Here's another undecidable question about context-free languages. Is the language also a regular language? We do exactly the same reduction from PCP, and one direction is easy. If there's no solution, then we just showed that the union of the complement languages is sigma star, and that's surely a regular language. But we also need to show the converse, that if L, the union of the complement languages, is something other than sigma star, then it's not a regular language. Suppose we have a solution to the PCP instance, and in particular, let X be the index symbols in reverse. That gives you the solution, and let W be the string you get by using the first string from each of the indexed pairs in order, or obviously equivalently the second string from the same pairs. Now, let H be the homomorphism defined by H of 0 is W and H of 1 is X. Remember, L is the union of the complements, the strings that are not solutions to the given instance of PCP. We claim that 0 to the n, 1 to the n, is not an L for any n, because if we repeat a solution to a PCP instance any number of times, we also get solutions to that instance. However, H of y is an L for any other y. That is, H of y is not a solution. This point requires a little thought. First, if y isn't zeros followed by ones, then H of y isn't of the right form to be a solution to PCP. That is, it will not consist of PCP instance symbols followed by index symbols. But if y consists of n ones preceded by a different number of zeros, then it can't possibly represent a solution. H applied to the n ones gives a particular sequence of index symbols. But we know the PCP instance symbols that this sequence of index symbols corresponds to is H applied to n zeros. Therefore, it couldn't also be H applied to a different number of zeros. So if L, the union of complements, were regular, then H inverse of L would also be regular, because regular languages are closed under inverse homomorphism. And the complement of H inverse of L would be regular because regular languages are closed under complementation. But this language we just argued is the set of 0 to the n, 1 to the n, such that n is at least 1, a language we know very well not to be regular.